Well, thank you, Greg, and thank you all for coming tonight. My pleasure to be here. So I'm going to talk to you a little bit tonight about biology. Now, I'm not a biologist, I'm a physical chemist, but I have studied the structure of biology at a molecular level quite a bit. And I've done some research on the origin of life. And it's a very fascinating subject, one that's near and dear to my heart. And I just want to share with you, just kind of at a very high level, what we can learn from examining the biological kingdom. And then if we try to analyze what we know about the biological kingdom in light of different models of origins, what are we going to learn? So the outline that I'll follow is shown here. We'll start by trying to define life at a molecular level, and then we'll go from the molecules to the size scale of whole organisms, and then look at life at the macro scale. And then we're going to talk about probably the most important subject in this whole business, and that is the origin of biological information. If you can explain the origin of biological information, you can in many ways explain why biology is what it is. And then along that line, we'll take a look at two completely opposite models of the origin of that information, the Darwinistic model and the design model. And then we'll take a look at a key aspect of biological systems called irreducible complexity. And then we're going to talk about, very briefly, about a quantitative objective test that we can apply to anything to see if it looks like it was designed. And then we'll talk about a key aspect of any good theory of origins, and that is falsifiability. And then finally, we're going to spend a little bit of time on an important takeaway for us as Christ followers. Okay, so before we get into it, I want to take just a minute, make sure everybody's on the same page with regard to something I'm going to do a lot of tonight, and that is I'm going to throw numbers at you that are expressed in scientific notation. And so just to be sure that everybody knows what we're talking about here, if we want to take the number 100 and write it in scientific notation, we write it 10 squared. 1,000 is 10 cubed. 100th is 10 to the minus 2, and 1,000th is 10 to the minus 3. So you can basically express some very large or very small numbers in a finite amount of space using scientific notation. So just to give you an idea, let's take sand. And if you go to the beach or to the nursery and you get some sand, and say you get a yard of sand, and you'd like to know, I don't know why you would, but how many grains of sand are in that yard? Well, on the order of 10 to the 7th, which is 1 followed by 7 zeros. On the other end, going small, take a red blood cell. What's the size of a red blood cell? Well, it's roughly 10 to the minus 4 inches. And then to go to the extreme limit on probably the largest meaningful number, physical number in the universe, and that is the number of particles, elementary particles in the universe. It's on the order of 10 to the 97th power. And as you can see, I may have lost track of my zeros there, but that takes a lot of zeros to write out 10 to the 97. But I am going to be throwing some numbers at you, and so just make sure that that's what you're seeing when you see those numbers. That's what they mean. Okay, how do we define life at a molecular level? Well, one definition that you could put forth is the following. It's a code. It's a code that can maintain itself and perpetuate itself. And that code is the genetic code. It governs all of life at a very fundamental level. It's like an alphabet. It's like words and sentences and paragraphs made up from an alphabet that's got 4 letters in it. And it is expressed in words and in paragraphs and in whole books, which are right on the backbone of a molecule called DNA, which stands for deoxyribonucleic acid. And so DNA is a double helix structure. It's shown up here. And so each of these individual strands in the double helix has a bunch of these 4 genetic letters bonded together with basically some sugar molecules and some phosphate molecules. And so it's like a string of letters that's wound up in a double helix. That's DNA. But there's also another kind of nucleic acid called ribonucleic acid, RNA, which is a single-stranded molecule. And it's almost the same as DNA, except it has one different letter. Instead of having the molecule thymine, it has the molecule uracil. But other than that, it is also a 4-letter language, if you will. And so what happens is the letter sequence, how these A, G's, C's, and T's, how they're lined up on a DNA strand, that determines the genetic information that that particular molecule is carrying. And genes are sections of DNA that code for particular proteins, because much of what the cell does is to make protein. And that's part of its business, big part of its business. If you take a look at how the information is packed, it's really amazing. What we find is that there are something called nucleosomes, which are basically, they are DNA molecules wrapped around little balls of protein. That's these guys up here. And then chromatin is a bunch of these nucleosomes hooked together with DNA linkers. And so it's kind of like a string of beads in a sense. And then what we find in actual chromosomes is that these chromatins are packed together, as you see here. So this whole section is packed like that. And then as you pack even denser, you end up with a final chromosomal structure, which has an enormous amount of information in it, shown down there. Okay, now a little bit more of a look at these molecules up close and personal. The DNA, so basically here are the individual strands, and this is very schematic, it's just ball and stick kind of thing, but each of these little colored line segments here, that is one of the 4 nucleic acids. That is one of the 4, heterocyclic bases that bond together. So what we find is that there's a complementarity. That we have bonding between A and G and between T and C on the DNA molecule, and that gives good strong bonding. Here's this actually shows the positions of the individual atoms in DNA. Well, what DNA does is it makes proteins, which are different kinds of biological polymers. Polymer, by the way, many units. Poly means many and mers means units. So both of these are many units, in this case of the individual base molecules, here of what are called amino acids. There are 21 or so amino acids that are important to life, and these are strung together in a linear string. There's no double helix here, and then they wind and fold to take on different shapes. And so, for instance, here's the here's the protein insulin. Okay, and what happens? The reason that they can take on their shape is that every so many amino acids, there is a critical amino acid, which, depending on its chemistry, can either be positively charged, negatively charged, or neutral. And that can then be attracted to other parts of the DNA that have a like or opposite charge to give the thing its shape. And its shape is what determines its biological function. Okay, so in the cell, there are basically 2 assembly lines that are going on all the time. One of them is protein synthesis. And in protein synthesis, what happens is within the cell nucleus, a nucleic acid, a messenger RNA it's called, is generated, and it is sent out to a place called the ribosome. And in the ribosomal area, what happens is the sequence of the genetic letters in the DNA code for the individual amino acids that go into a protein. And as we'll see in a minute, it takes 3 heterocyclic bases to code for one of the amino acids, and that's how that works. So you have this information coming out from the cell nucleus, and the sequence of base molecules in the RNA determines the sequence of the amino acids in the protein. And so there are about 60 different proteins that actually catalyze this process. So it's very synergistic. But this is one of the 2 assembly lines. The other one is DNA replication that happens whenever a cell divides. And so what happens here is that a protein clips the DNA, so to speak. It gets it to unwind and like so, and then a copy is made from the uncoiled DNA. And this is a process that's catalyzed by many different kinds of proteins. And it leads to then the creation of a new copy of the DNA, which is passed on to the daughter cell. And that goes on all the time in every living organism. Okay, a little bit on this genetic code now. Interestingly, only about 1% of the DNA is actually involved in protein synthesis, but it's a very important function. And so the way the genetic code looks is there are basically 3 different bases in a triplet of bases that's called a codon. And so what you find here is this first base, second base, and third base. No baseball pun there. And you have to have at least 3 bases if you want to code for the 20 amino acids, because basically you've got 4 choices, and you need 3 of them because 4 to the third power is 64. So 4 to the third, if you have 3 of them, you could code for up to 64 amino acids, but you don't need to. You only need to code for 20. But by using 3 bases and having 44 leftovers, so to speak, there is some redundancy. So for example, if you take a look in this here for this in the serine column, the first base is always U, uracil. The second base is always C, and the third base can be either U, C, A, or G. It can be any of those 4 molecules, and all of those combinations will code for serine as an amino acid. There's also, if you take a look at genes, there's actually overlap in the information that's coded there. And to give a kind of a homely analogy, we can make an analogy to Morse code. So here's a section of Morse code. There's actually 2 different messages in that section of Morse code, depending on where you start. If you start at the beginning, you spell the word manna. But if you start in a few characters, you spell the word mini, just by phase shifting a little bit. And the same thing works in DNA. So this very efficient, tight packing of information with overlapping information in different sections of DNA. And then finally, different proteins do different things as well. Some proteins can do multiple jobs, and this adds to the efficiency of the overall system. And by the way, I forgot to say at the beginning, at any point you have any questions, just put your hand up, and we'll take them as they come. Yeah, Dan?
I find my heart racing because I keep thinking there's going to be a test at the end. There's no test.
No test.
Right, okay,
Yeah, right. All right, so that's the molecular scale. Now let's jump up to the macro scale. Okay, where do we go? Well, let me tell you, there are millions upon millions of species of animals and plants on our planet. And we discover about 10,000 new species every year. And so there are literally hundreds of millions of examples that we could point to that are just phenomenal. And I'm just going to give you a very, very few of them. I'm going to start with the human body, because I think the human body is just fascinating. And so I love athletics. I used to be a gymnast when I was in high school, and so every time the Olympics comes around, I'm riveted to my TV when the gymnastics come on to watch these guys do their thing. So much phenomenal flexibility. But you know what? It's not just us that are flexible. I mean, there are other creatures that are flexible too, and some of them are trying out for the Olympic team. And all of this can happen because of the coordinated action of biological subsystems within the human body. And all of that can happen because of the operation of individual cells that are ultimately determined, and their function is determined by the genetic code. Because the cell is by far and away the most sophisticated nanoscale factory that has ever been seen. Nothing in human engineering can rival the cell. And it's the coordinated efforts of lots and lots of cells that allows the human body to do what it does. So let's take a look at just some facts about the human body that you may or may not know. Okay, first of all, there are 37 trillion cells in an adult human being, 200 different kinds. There are about 60,000 miles of blood vessels. If you were to string them together end to end, that would go around the surface of the globe 2.5 times, just in your body. Every day, your heart pumps about 2,000 gallons of blood. Over the course of a year, that would be enough to fill an Olympic-sized swimming pool. And if we treat our hearts well, they can last for 80, 90, 100 years. There are 640 skeletal muscles connected to bones. There are 7 meters, 23 feet of intestines that absorb nutrients from food so we can function. Our brain is the most phenomenal computer that we know anything about. There are 1 billion neurons, nerve cells, in an adult human brain. And at any one time, they're connected to 1,000 other neurons. And when a person is in an active learning mode, the brain is constantly rewiring when you're learning, even when you're reading the newspaper. Anytime you're using your brain at all, rewiring is going on. But the more you're using your brain, the more rewiring is going on. There are thousands of chemical reactions going on all the time in every one of our bodies. And so they allow us to grow from a single cell, single embryo, up to a human being, fully developed baby, and then We grow, we are born, we can eventually reproduce ourselves. We can maintain ourselves. We can fix ourselves, so to speak. Every now and then I look at a ding on my car and I think to myself, man, I look at the ding on my car, then I look at the last cut that I had that's all better now, and I go, wouldn't it be cool if somebody would develop self-healing car surfaces? They'd make a mint. But it's just amazing that this happens, and we take it for granted because we just don't think about it. We can respond to our environment. If you find yourself, if you're used to being in a cold place and you suddenly get put in a hot place, you're pretty miserable for a while, but after a number of weeks, your body changes considerably, and you get to the point where you can function in that hot climate and vice versa. And then we can do some amazing things again, athletically, mentally, artistically. And so again, just to take the athletics analogy, people can run fast, they can swim fast, they can dive well, and they can hit a ball that comes at them at 100 miles per hour. It gives them about 0.3 seconds between the time the ball is released and the time that guy has to make a decision whether or not to swing the bat, and if so, where to put the bat. 0.3 of a second. And how anybody can hit a 100-mile-an-hour pitch is beyond me, but there are guys that can do it, as we all know. So there are many aspects that we could talk about, but I want to talk about one that, again, I think many people take for granted, as it just sort of happens, but when you look at the details, it absolutely is amazing, and that is human reproduction, how that actually happens. So, as you know from biology, you have a sperm that penetrates an egg, and the egg, the ovum, has 23 chromosomes, half the genetic material from the mom's side. The sperm has the other 23 chromosomes, and it's in the male sperm swim in a fluid called semen. And so when you get fertilization, that's called a zygote in biology. And the process by which this happens is nothing short of phenomenal. So what we find is that these little sperm cells, they're basically, there's this head up top here that is got some corrosive chemicals in it. And then there's this tail that whips, and that's how the sperm swims, through the semen. When the sperm is still in the male, there's a special barrier that keeps the sperm out of contact from the male's blood. And that's a good thing because the male immune system would attack and kill the sperm if that barrier wasn't there. The vaginal area of a woman is normally acidic, and there's this little mucus plug that normally blocks the entrance to it. Well, what happens during fertilization is that some chemicals in the semen actually neutralize the acid so that the sperm won't die, and it thins the mucus plug a bit so that the sperm can swim through it. There are other chemicals, or all kinds of chemicals in semen, but there are some other ones that temporarily deactivate the woman's immune system, because if that didn't happen, then her immune system would attack the sperm and kill it almost instantly. But that leaves the woman prone to infection. So there are yet other chemicals that kill the bacteria that might otherwise multiply in the woman. And those chemicals are also found in the semen. There is normally a fluid flow mechanism that keeps stuff, particulates and things, away from the sensitive part of the uterus. But what happens during fertilization is that mechanism, that flow, is actually reversed by some other chemicals in the semen. And that allows the sperm to get actually drawn in to where the eggs are. And then there's these chemicals in the uterus that actually activate the head of the sperm so it can release its corrosive chemicals. And those corrosive chemicals weaken the membrane of the ovum so that the sperm can get in. And that's shown here. Once this occurs, once there's fertilization, then the zygote releases a bunch of sodium, and what that does is it blocks other sperms from entering. And then finally, there are other chemicals that are released that remove any other sperm from the zygote surface. So you have one egg, one sperm, fertilization. Once that occurs, then you have a miracle. You've got a completely unique human being, unlike any other that has ever been born before. I will point to this little guy. He is one of my grandsons, and that's his picture when he was born. So he's not quite as serious as these other guys who are a little bit more posed. So if I were to bring some kind of engineering invention to you that could do anything like this, you would be impressed and you'd probably buy stock in my company, yes? Right? And yet, most people on the street, if you ask them and pull them aside and say, yeah, what do you think of this? Many people go, well, yeah, and it happens a lot. There's a lot of people in the world, and they just don't think about it. But if you think about the implications, if you think about the coordinated chemistry between the semen and the uterus, that area, and all the stuff that goes on, you just can't help but think, my goodness, this looks like it was designed. Okay, so we can make an analogy. When we think about the human body, we can make an analogy. And this, I'm going to give you lots of analogies because as you're talking to your friends, you're probably not going to remember all the detailed biology. But analogies are very helpful. So here's one that you can use with your friends. Here's the tallest building in the world. It's in Dubai. And if you saw the Mission Impossible movie, you remember Tom Cruise hanging outside of that when the sandstorm goes by. Pretty dramatic. Well, let's suppose there's a laptop. And in the laptop, there is a file structure. And this file structure contains information on how to make every single item that goes into that building, everything. And then also instructions on how to assemble them all to make a building. Well, this is analogous to the genetic code, and also to epigenetic programming, which I won't have time to talk about tonight, but there's several levels of programming in the cell that go above the genetic level that determine function and structure. So all these instructions would be like this. Okay, this is the information, this is the cell, if you will, the individual information parts of the cell, and here's the final product. Okay, so how in the world did all of this information come about? Well, we basically have two choices. Either it's purposeful design by some intelligence, or it's spontaneous generation without a plan. It's really one or the other. There really aren't any other choices as far as I can tell. So let's start with the naturalistic, purposeless, no design model, which ultimately goes back to Charles Darwin. And so Charles Darwin, in 1859, wrote a very important book, very influential book called The Origin of Species. And some of the basic ideas in the book are that chance changes would lead to natural selection, which would lead to smaller changes or microevolution. And if you extrapolate that to larger changes or macroevolution, you would have bona fide change in an organism. So he proposed a phylogenetic tree, as he called it. Down here at the bottom is the original life. And so this is variation in size and in shape, and this is time going this way. And basically, as generations come and reproduction occurs, there are changes, and these changes eventually, if they're selected for, they lead to new species, and you end up with this tree of life. And up here at the present, you have all the species coming from this original source. And so he believed that everything came from the originals, which are down here. At the time, in 1859 or so, we didn't know much about biology. In fact, we were incredibly naive about how complex biological systems are. And so, for instance, Darwin thought that vision was really simple, and people thought that cells were just nothing more than globs of protoplasm. They had no concept. Genetics hadn't even been developed yet. It was being developed at the same time, but it wasn't done. And so out of Darwinism comes neo-Darwinism, neo meaning new. And so this happened in the first half of the 20th century, and it's also called the Great Synthesis, or the Darwinian synthesis. So it's Darwinism, the original ideas, plus what we know from genetics, paleontology, anatomy, embryology, physiology, and so forth. Many aspects, many different sub-disciplines in biology coming together to make what's called neo-Darwinism. And it remains the leading model of origins in academia. Okay, so some basic ideas in neo-Darwinism is that it's mutations that give rise to small changes, and these are selected if they give reproductive advantage to the species. There is no limit to the extent of biological change that's possible in this model. Small changes accumulate over time, leading to big changes. And so you have the spontaneous origin of biological complexity without any design being required. That's the idea. So let's take a look at the mechanism whereby these changes are thought to occur. So here's our genetic code. Here are the 3 different bases, each coding for a different amino acid. And there's our proteins again. And here's our cell division and making a copy of the DNA. Basically, a mutation is just a copying error when a DNA is copied. And so it's random changes in the letter sequence that occur during the making of a copy. And these changes are then transmitted to the proteins that are made by that DNA, because if you change the order or the sequence or the chemical identity of a particular base molecule, you're now changing the sequence of amino acids in the proteins. This is thought to give rise to new biological functions. And that then, if those changes that occur, if the new functionality give you reproductive advantage, which is a key idea in Darwinism, that is, you can do better, survival of the fittest, so to speak, then these changes will be selected for by the natural environment. And so out of that is going to come new organisms, new species, all the way up. In other words, the entire biological kingdom will be coming from this process. But let's take a look. What are the odds of it really happening? For a long time, people were limited to doing computer modeling, and this has been going on for 50 or 60 years, actually more like 70 years actually. Lots and lots of computer modeling, to which biologists all said, you're stupid computer. I don't care about your computer simulations. This is biology. It's different. It doesn't do what your computer simulations do. Well, there was a major breakthrough a few years back. A very bright young biologist by the name of Douglas Axe, who actually lives over in Seattle now. He did a very good piece of work when he was still at Cambridge, where he took one protein, just one protein, and it's called beta-lactamase. It's the protein that gives penicillin its resistance to antibiotics. And he asked the question, how many different possible configurations of this protein are there that would work biologically? In other words, that give you the right shape and function to be able to give you the ability to fight off penicillin. What he came up with is that there was only 1 out of 10 to the 77 possible sequences that would give you the kind of structure it would take to give you resistance to antibiotics. Well, Hugo de Vries, who was a Dutch botanist back in the earlier part of the 20th century, had a great sentence. He said, "Natural selection may explain the survival of the fittest, but it cannot explain the arrival of the fittest." And that is so true. You're not going to get there from here. Okay, why not? Because the closer you look at mutations, the less desirable they are from being able to get done what you want done. So mutations, they do occur, to be sure, but they're actually pretty rare because there are built-in repair mechanisms in the copying of DNA. And so it's only about one mutation or one copying one copying mistake per 10 billion DNA genetic letters being copied. So it's a very small occurrence. Mutations typically cause only very small changes in the organism that's alive right then, not to mention their ancestors, and I'll talk about that in a minute, or their descendants rather. Okay, so mutations, they have to occur in a germ cell in order to be heritable, right? I mean, I can have a mutation, but it'll stop here unless it happens in a germ cell, in my case, sperm. It won't be inherited by my children. You also need lots of coordinated mutations in order to get a change in body plan, and these are extremely rare. In fact, they've been estimated to be no more than about one coordinated pair of mutations per 100 million years in the life of a given species of mammals.
So by coordinated, do you mean in both the male or female?
No, I mean two different mutations in germ cell on either side that work together to give a change in body plan. Okay, so it would be just within one of the sexes. Okay, so the thing about this is that if a mutation is going to make a change in a body plan, it's got to be expressed early in the embryonic development, so it's got to happen early. However, early mutations are virtually always harmful or even lethal. Okay? So here's some examples. Here's fruit fly with a mutation so that he's blind. He's got this grotesque head and this very dysfunctional eye. There's a fish that's obviously got a problem. And here's a dog that's got a triple problem. Okay? So there's mutations for you. These are ones that were heritable. These are ones that occurred early in embryonic development. And as you can see, they are not helpful. So beneficial mutations that are required for evolution to go forward to make new body plans, they generally don't occur. In contrast to that, the mutations that do occur, the ones that happen later in non-germ cells, they are not useful for making new body plans. So you just don't have the right combination. You don't have them happening where they do occur, where they are needed, and they do occur in places where they're not needed to make new body plans. And then the mutations also do not introduce new genetic information into a gene pool. They allow you to maybe rearrange what's already there, but there's no new information added, and in fact, the information is usually degraded as a result of mutations. And then, to add insult to injury, we have artificial breeding. Okay, it's something that we can do to try to make organisms change. It has shown us very clearly what the natural limits to biological change are. So, how much information, I'll have more to say about that in a minute, how much information are we talking about, though, is going to be required to get from, say, amoeba to man? Well, we can take a look at some different forms along the complexity spectrum. We'll just take three. We'll take a simple bacterium that's got typically 6,000 genes or so. We'll take a look at a fruit fly that's got about 14,000 genes. And by the way, 6 million genetic letters here, 65 million genetic letters here. And then go all the way to humans that have 20,000 genes and 3.2 billion genetic letters. We'll make a very simple approximation, and that is that a gene is either on or off. It's either activated or it's not. So it's a binary thing, on or off. The minimum complexity increase, making that simplifying assumption, is going to go as, to get from simple bacteria to human, it's going to go to 2 to the 20,000th power, because that's the number of genes, divided by 2 to the 6,000th power, or 2 to the 14,000th power, or a very, 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 very big number, 10 to the 680. Remember, there's only 10 to the 97 particles in the whole universe. This number is approaching infinity. But that's the increase in complexity it's going to take in order to get from a simple organism to a full-fledged human being.
That last one's just not natural.
It's not what?
That last one, picture on the bottom, that's not natural.
Right? Yeah. There's a mutation in that back, right? All right. Let's talk a little bit about irreducible complexity. Very important concept. Originally introduced by a man by the name of Michael Behe. He's a biochemist at Lehigh University in a very influential book that he wrote many years ago called Darwin's Black Box. And so the idea here is the following, that if a system is irreducibly complex, if it's composed of 2 or more necessary components, and if you remove any one of those components, the system ceases to be functional, then it's irreducibly complex. And in his book, he gives 3 really good examples. One of them is really simple, a mousetrap. One is a bacterial flagellum, and one is blood clotting. So we'll talk about each of these quickly. So mousetrap. We all know what's in a mousetrap. Various components all mounted on a piece of wood. You got a catch, you got a holding bar, you got a spring, you got a hammer, you got some bait in there too. You know very well that if you take away the spring, you will not catch a mouse. If you take away the holding bar, the thing will not close. If you don't have a hammer, there's nothing to catch the mouse. And if you don't have a platform, then the pieces just can't stay together. So this is irreducibly complex, because if any one of those 5 components is missing, broken, or the wrong part, the trap will not trap a mouse for you. Very simple. Okay? And you can't really build a mousetrap by natural selection because you have nothing to select for until it's all done. Right? There's no advantage to 4/5 of a mousetrap. You get no benefit from that. It's got to be all done, and then it'll work. All right, let's take a look at bacterial flagella. Okay, these are basically little whipping tails that allow bacteria to move through fluids. And so you have this very sophisticated motor. You've got a propeller, And then you've got basically down here, you've got a bunch of proteins that give you the elements of a human-made motor. You've got stator and studs and rotor and membrane and all these things. And so it very much looks like a human-made motor. And here is one of the degrees of motion. This is the one that's basically the circulating round and round motion. But then there's another one which is a whipping motion. And as these have been looked into, people have found that, clearly if you take away any of the components, it's not going to work. And there are about 100 different molecular motors that are functioning here. And it really is very analogous to a human-made motor. And so here's an example from a particular species of photosynthetic algae, freshwater. There's the flagellum. Well, as with the mousetrap, as I said, if any one of these components is missing, it will not work. It just doesn't. Then the third one that he talked about was blood clotting. Okay, so here's just a optical micrograph of a blood clot. And so you have red blood cells that are held together in the clot by these little fibrin protein meshwork that ties everything together, sticky kinds of things. And so the biochemistry of blood clotting is pretty involved. I'm not going to go into any of it tonight, but we're just going to say, okay, what's got to be true about a blood clot? Well, it's got to be located at the wound site, obviously. It has to be limited to the wound site, because if a blood clot gets away from the wound site internally, you could have a stroke or something worse. You could get a blood clot in your, in your veins. That's bad. It has to be strengthened to withstand impact if it's going to be able to, not hang on there long enough to do the job. And then when the wound is healed, it has to break itself up. Okay? If you don't have it, you're a hemophiliac. And so that's obviously a serious health threat. You could die. So let's imagine what life would be like if you didn't have blood clotting. Okay, well, obviously you'd bleed to death. You have to have all 20 of the proteins that make blood clotting work. They've all got to be present in working order in your blood. There are about 30,000 DNA segments in animals that do blood clotting, so there's a lot of possibilities for making these proteins. If we just take a look at one of the key proteins, it's called P-TA, or tissue plasminogen factor. This one, there are 4 different kinds of domains or structures for this particular protein, and there are about 10 to the 18 different ways that you could assemble these 4 different domains to make functional TPA. Let's suppose you try to make this stuff at the rate of 1 trial per second. The time it would take to make it at that rate of trial and error would be 30 billion years, which is quite a bit longer than the age of the universe. Well, let's suppose that we don't really need 10 to the 18. Suppose that only 1 out of 1,000 positions is important. Well, that cuts you down to 30 million years. Okay, that's within the age of the Earth. But that's just for one of the 20 proteins, and you need all 20 of them to work. And if you don't have all 20 of them working, you've got to survive without blood clotting, and that won't work. So it's irreducibly complex. You will die of hemophilia unless you have a fully functioning blood clotting system. And there have been many challenges to this concept over the 20 or so years since Behe wrote that book. And basically, they've all been shown not to hold water, because it really is a robust concept and it works very well. Okay, so neo-Darwinism basically has no reasonable explanation for the origin of irreducibly complex systems, because natural selection can't select unless it's fully functional and all there. Okay, let's talk about fossils a little bit. When Darwin wrote his book, he charged future generations of paleontologists. He said, all right, go out and find the fossil evidence to support my model. Well, that was a lot of years ago, and people are still looking, and it's not coming in very fast. So here is a snapshot of the geologic column, which is a hypothetical column of Earth that gives the different geologic periods, their ages, and different species of animals are found throughout here. The oldest here, the youngest up here, and evolution has supposedly occurred throughout the development of time across this period here. And so you can you can't find the geologic column anywhere in any one place on the Earth completely together. You have to go to different places to find different sections of it, but you can do that. And people have done that for years looking for fossils. There are three characteristics of the fossil record that are really important. One is called abrupt appearances in the Cambrian rock, so-called Cambrian explosion. Very sudden appearance in the Cambrian of the vast majority of all animal groups that we know about today. No predecessors in the Precambrian. They just show up. Second one is stasis, which means lack of large-scale change. Things come into existence and then they just go through time without changing very much at all. And I'll show you some examples in a minute. And then there is related to this, there is the absence of transitional fossils. Darwin predicted that there would be many gradual changes found in the fossil record, and they have not been found. Okay, so let's talk a little bit about the Cambrian explosion. So here is a diagram that kind of illustrates what's expected versus what's found. So Darwinian theory, the phylogenetic tree has, here's the beginning, and then Darwinian theory has all these branches growing up. What's found in the fossil record is basically things come into appearance suddenly, typically in the Cambrian, and then they go forward through time without changing much. And so it's straight up. Lines are straight up. They don't go like this. Here's another way of showing it. Here's the Darwinian model. Here's the reality. Cambrian explosion is here. Species come into existence, pretty much stay the way they are, and then either they remain with us to the present or they go extinct, represented by these shorter lines here. The Cambrian explosion is thought to have occurred over the period of time of about 20 million years. 20 million years is to the age of the Earth, 4.5 billion years, what 8 inches is to 100 yards on a football field. Okay, not much. So this is an enormously short period of time. 20 million years is an enormously short period of time for all this evolution to occur. All right, what about stasis? Well, basically, there are all kinds of species that we can find either alive today or they've gone extinct. They haven't changed much. So we call them living fossils if they're still alive. So we have aardvarks, haven't changed in 20 million years. Alligators haven't changed in 30 million years. Snapping turtles, 57 million years. Sturgeons, 80 million years. Sea urchins, 230 million years. Just some examples here. Fossils, modern. Fossil, modern. Fossil, modern. Hardly any change. What about the gaps? Well, they're very real. You might say that the fossil record has a bad case of gaposis. So again, here's the phylogenetic tree, and these dashed lines indicate missing fossil evidence to connect that to that. It's the rule. Darwinian expectation, reality. Lots of missing, the lack of a dot means there's just nothing there. Very schematic, but gets the idea across. Again, this is something that you can share, with your friends. Fairly easy facts to remember about the fossil record. Okay, but there are other issues as well. So, for instance, you have sequence problems. The distribution of the fossils in rocks typically is not at all what is expected based on the Darwinian model. And there are major size problems. That is to say that the actual sizes of fossils that are presumed in these different lines of descent are usually very different from what you actually find in textbooks. So for instance, this is out of an evolution textbook. This shows the evolution of a series of reptiles. And you can see that these smiley guys, as they go through time and they're evolving, that they seem to have fairly similar skull sizes. Well, if you look at the actual skull sizes, it's more like that. And that changes the story altogether. A little bit of poetic license went into the development of that figure. Okay, and then you have the time problems. That is, the different skeletons shown in transitional fossils or transitional sequences are oftentimes not found together geologically. They're just not close to one another at all. So you have to wonder, how could they have undergone this gradual change if they're not even in the same part of the world? And then the whole question of biological change is really important because there are really very strong limits to it. And so we've learned this from artificial selection. So now you're trying to selectively breed. You've got particular goals, things you want to accomplish. And so it's a really good way to test just how flexible, how plastic is biology anyway. And so Darwin actually used the idea of natural selection as the agent of change. And he pointed to artificial selection as a great example of natural selection being pushed along a little bit. But what are the realities of it? Well, the realities of it are quite a bit different. Well, first of all, the goals are different. So there are no goals in natural selection. You've got preconceived goals in artificial selection. Natural selection is very passive. It just is thought to happen. In artificial selection, it's active. You've got people doing the breeding. And then you can go through, you can make changes fairly quickly in artificial selection, but it takes lots of time in natural selection. But what we found in artificial selection is that the change is really limited, even with all this intense effort. So for instance, if you take a look at sugar beets, okay, 75 years of trying to increase the sugar content in sugar beets. And in 75 years of intensive work, it was increased from 6% to 17%. And then it plateaued. No more was able to be had. Dogs, okay, the weight of a dog across the species is going to be as little as a few pounds or as many as 150 pounds. But you're not going to get any heavier than 150 pounds. No matter how hard you breed your big dog, you can breed him with another big dog down the street and he's not going to get any heavier than about 150 pounds. People have tried and it doesn't work. The size of fruit, okay, how big a plum would you like to make? I'd like to make a plum as big as a grapefruit because I love plums. People have tried to make bigger plums. They don't get any bigger than what you find right now. They limit out. And so it goes. There are very strong limits to biological change. And then as we look around, we find stable adaptations, which is something that causes species not to change, even if they wanted to. And these alone are a great statement. And so it's the ability of an organism to survive and thrive in a particular environment. And again, bazillions of examples we could point to, but let's just take a look at a woodpecker. Okay, woodpeckers have 2 front claws, 2 rear claws, so they can stand on a tree and have vertical grip. Then they have these really stiff elastic tail feathers that actually let them stabilize. That's kind of like a tripod. They can put those down as well and really hang in there. Then they have this rapid fire head that goes back and forth as they peck away. And the muscles for that are phenomenal. And then they have they have some cartilage between their beak and the back of the head that acts like a shock absorber. Because imagine beating your head against a tree all day long to get your dinner. It would hurt. Well, it doesn't bother these guys. And then their tongue. They have a long, barbed, sticky tongue that can go inside the tree trunk. And there's this drive mechanism that allows the tongue to extend 3 to 5 times beyond the length of the beak, shown there. Stable adaptations everywhere. How do you explain them? And they're certainly going to resist change anyway. All right, so how could we think about this from a design framework? Okay, if we say to ourselves, okay, I just don't think this is happening by accident, how can we think about it? Well, here's one way to do it, and this is one that I've kind of settled on. So the extent of change that biological systems exhibit is limited to a level that is going to be well below what's required to go from amoeba to man. In other words, change is limited. That seems clear from artificial breeding. The extent of change is limited by the available genetic information. And that's what limits you. So the biological kingdom originated with intelligent design and creation of a wide range of fully functional species over time. And those originals, the ones that came first, they gave us the blueprint for the present biological kingdom. And so the speciation has occurred. As it's occurred, it's because of the amount of genetic information that's there, the richness of it that was present. And this gives us a framework that allows us to think about the biological kingdom from the point of view of a theist, a Christian, if you will. One who says, yes, I believe in an infinite personal God who is involved in creation. And when I look at the fossil record and I see the Cambrian explosion, you see creation, 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 and then going forward, functioning well, unless they go extinct. Well, a lot of times when I give this kind of talk to unbelieving audience, they go, well, you're just laying your religious baggage all over my science. Don't do that, please. And I say, now, wait a minute. Okay, can we be objective about this? Is there an objective test for design? So it isn't just religious proclivities. The answer is yes, and it goes like this. We're going to take a look at sequences, and we're going to ask the question, can you detect design in a sequence? And so by a sequence, it can be a string of letters, like my dog has fleas. It could be a string of numbers, like that. Might be somebody's phone number. It could be a string of molecules, like in DNA. And William Dembski, who is a mathematician and a philosopher, both, wrote a couple of books a number of years ago that are very, very helpful here, in which he developed specific criteria for design in a sequence. And they are basically twofold. If a sequence is designed, it's going to have a very high degree of complexity, for one thing, which is equivalent to saying it has a very low probability of formation. And then it's going to have a very high degree of specificity, which means that it can be identified by means of some pre-existing pattern, and that it communicates specific information. So let's take a look. Let's test this with a couple of things. These together are the design test. So let's take this series of letters. Okay? That particular sequence of letters has a certain probability of formation, and it's basically given by the number of letters that are there. It means nothing, at least in English, right? However, if they're rearranged differently, it means something. Now, which of these passes the design test? Well, do either or one or the other or both of these, do they have a low probability of formation? Yeah. 26 letters in our alphabet, there's 13 letters there. So the probability of this particular sequence of letters, if you pull like Scrabble letters out of a hat, the probability of getting this particular sequence is 4 times 10 to the minus 19. Pretty low probability. But does either of them pass the specificity test? Identifiable by means of a pre-existing pattern and communicating specific information. Clearly this one does not, because it means nothing in English, using English as the filter. This one does. This one passes the design test, this one does not. Okay? That's how you can tell if a sequence has been designed. So a couple of examples, just for fun. Ping pong ball toss, all right? So let's suppose we have 149 glass jars, and then we have 41 colored ping pong balls. And we got blue ones, or green ones, pink ones, and orange ones. We are now going to drop those in a minute. 1 minute, we're going to drop in all 41 balls one at a time like this into the series of jars. Well, let's suppose that this experiment happens, and after 1 minute, you get something like that. You go, yeah, makes sense. Random distribution of the colored ping pong balls. Just what I'd expect in the absence of design, putting the balls in particular jars. But what if after 1 minute you got that? And I told you, yeah, we just dropped them in. Would you believe me? No, it just doesn't compute, right? Because you know darn well, because of the probability of formation being so low for any of these, to have one come out with information in it, there are so few of the many bazillions of possibilities that carry information that you know that if one shows up that carries information, it has to have been put there by someone with a mind. So the probability of getting this one or the one before, they have the same probability of formation. It's about 3 times 10 to the minus 55th, okay? That means that you would have to try doing this about 10 to the 54 times before you would actually get hay by chance. Well, we only have about, if you do this once a minute, it's going to take you 10 to the 54 minutes, and I can tell you that's a lot longer than the amount of minutes we have since the age of the universe. In other words, this will not happen unless somebody deliberately puts the balls in there. That's the design test. All right, so there's the odds of getting that over the age of the universe. Pretty small odds. All right, so let's talk now about falsification. Very important idea in any legitimate scientific theory. Falsifiability means that you can think of a test that you could apply, which, if the idea failed that test, meant that the idea was false. Darwinism is not falsifiable. Darwinism is so slippery, you can explain anything with Darwinism. I mean, you could say to a Darwinian, for instance, you could say, now how in the world do you explain altruism in people? That doesn't make any sense. If we're just out for survival of the fittest and get my selfish genes out there and I just want to propagate my species, my race, whatever, why should I be good to anybody else? Why shouldn't I just fight for what's mine? And they would say something like, well, I guess that's reasonable, but we're here and we're altruistic, so it must have happened. And there must have been some selection pressure on being nice, because if nice people didn't get along, they couldn't form tribes and so on and so forth. And you can do that. You can come up with and design, people call them just so stories, just like Rudyard Kipling. You can come up with just so stories to explain pretty much anything using the Darwinian concept. But in contrast to that, the design model is falsifiable the following way. If you want to falsify the design hypothesis, all you have to do is to demonstrate that a high information system, like a cell, can assemble itself in a finite amount of time through chance. Okay? And you can think of lots of ways to try to do that. The one we just talked about, dropping the ping pong balls in the jars. Here's another one. Let's take a Scrabble game, and let's put some letters out on the Scrabble game. And you have to kind of use your imagination with me here. Let's suppose that instead of just sitting on a flat board, each place where you can have a letter is actually, there's a little hole in the board, so the letter will stay there and it won't go like this. Let's suppose you come up and you just bang that thing like this, so all the letters jump up and come down someplace else, and they all land in those little holes. Okay, so there's that combination of letters. That's the way we start. And then let's suppose we think about that particular rearrangement of this combination of letters. Okay, how long do you think it's going to take? If I'm banging this thing once a second, how long do you think it'll take before I have even a 50-50 chance of getting that? Anybody want to take a guess?
More than 12.
12 what?
Yeah, more than 12 times. Yeah.
More than 12 times? Yep. More than 12 seconds. That's definitely more than 12 seconds. Anybody want to just proffer a guess on the number of years?
12 millennia.
More than 12,000? Yeah. Anybody want to go a little higher? 14 billion, 14 times 10 to the 9?
1 times 10 to the 57.
1 times 10 to the 57th, what unit? Years. 10 to the 43rd years. You're a little high. But you're in the right neighborhood. 10 to the 43rd years. Banging this thing once a second to get that. Okay, so this illustrates the kind of test that you can apply to see if the design hypothesis is falsifiable. Just come up with something like this. It doesn't matter what it is. It doesn't have to be coming up with making a cell. Just show that a high information system can happen by making random changes in this letter structure in a finite amount of time, and you will have falsified the design hypothesis. But to the best of my knowledge, nobody has done that. Okay? All right. Takeaway for us who love the scriptures. Isaiah 46, 9 through 10. Remember the former things of old, for I am God and there is no other. I am God and there is none like me, declaring the end from the beginning and from ancient times things not yet done, saying my counsel shall stand and I will accomplish all my purpose. Okay, this is one of many verses in the Bible that talk about the omniscience of God, his infinite knowledge of all things. The scripture is so humble. I mean, it understates things so often, and it really understates the omniscience of God. Because as I said, there are 10 to the 97 elementary particles in the universe, and that doesn't include dark matter. If God is omniscient, and it takes a quantum mechanical wave function to describe the behavior of every particle, God knows the wave function of every one of those particles, 10 to the 97 of them. There are roughly 10 to the 33 genetic letters in all the nuclei of all the cells of all the humans on Earth today. If God is omniscient, he knows every single genetic letter in every human being, every cell of every human being on Earth. And he knows how that person is made. And again, you know, the statements in the scripture are so humble in comparison. And Jesus said, you know, the number, even the number of hairs in your head are numbered. Okay, that's an understatement. It says so much more than that. His knowledge of our bodies is complete and perfect to the point he knows every genetic letter in every cell. There have been about 10 to the 17 seconds, roughly, since the universe began. God knows what has happened in every one of those bits of time, in every place in the universe. His knowledge is infinite. So he's all-knowing, he's all-powerful, he's all-wise, he's all-loving, he's all-just. Bottom line, he's in control, and he can handle our stuff. All right? We all have stuff, right? Things that keep us up at night. Wake up at 3 in the morning and, oh, I don't know what to do about that. God can handle it. He wants us maybe to have a part in handling it. He wants to walk with us. But because of his knowledge, we can rest in his ability to help us navigate life. And we can do so with peace in our hearts, knowing that not only does he know everything, but he's all good and he's all powerful. He can make things happen. He can keep things from happening. And whatever happens, he is in complete knowledge of. And so even when the hard things of life hit, and we don't know why they happen, we can rest in the fact that God, he wasn't surprised by that. He knows what he's doing, and we can rest in that. All right. Well, I went over a little bit here, so let me just stop and be happy to take any other questions you might have on any of this. Craig?
Yeah, Scott, so you started off by early in the lecture saying that the neo-Darwinist synthesis is the predominant view in academia today.
Yeah.
So what do they say about this? Why is this not compelling to the predominance of biological academia?
They say several things. One of them, they say it's not science. As soon as you appeal to the supernatural, you're no longer doing science.
But you haven't appealed to the supernatural until this slide.
Okay, or to anything, let me say, you're appealing to the extra biological. As soon as you go above the actions of any known life form, you're now appealing to something that you have no scientific knowledge of, is the way the argument goes. But the problem with that is it depends on how you define science. Most people would define science as that set of naturalistic explanations that can give you some understanding of something. In other words, it's limited to natural phenomena, natural meaning cause and effect, things that I can see directly happening as a result of the laws of chemistry and physics. The better definition of science, I think, is coming up with the best explanation of something, wherever it leads you. And so to basically take some of these numbers and say design gives you a understanding of how this could happen when you know chance can't do it. That, to me, is a perfectly good scientific statement because, in fact, Darwin even talked about it in his book. He talked about basically using phenomena that go on in the modern day to explain things in the past. It's the short phrase of it is the present is the key to the past. So if we are trying to understand something that happened in the past, the best explanation is going to be one that we know is operative in the present. So if we know, for instance, that high information systems like the Dubai Tower do not happen apart from smart engineers working on it, there's no reason we can't apply that logic to the origin of something far more sophisticated, the human body or whatever you want. So that's one thing. Another thing that they say is, well, it's just religion in disguise. It's what's the phrase? Creationism in a cheap tuxedo, stuff like that. A lot of kind of slanderous kind of statements. But bottom line is, if people are locked into naturalism, metaphysical naturalism, they're going to say to you, sorry, I can't buy it because it's not natural. It's not, it doesn't obey the criteria of a natural, quote unquote, explanation.
Just curious if you, well, two questions. The second one is, have you ever been successful at getting a naturalist scientist to rethink their position? The first question is,
given, something that's come out of all the conspiracy theories and whatnot that float around is that it was like one principle I've seen stated is you cannot make somebody believe something they do not want to believe. They will come up with a theory, a conspiracy, or even an outlandish explanation that doesn't make sense to anyone else.
Yeah.
But, compared to a set of logical handcuffs, they need any kind of key at all to unlock those handcuffs
Yeah.
and say, I don't have to believe that. So
Yeah.
how do you get past that?
Okay, that's a great question, Wayne. First of all, according to Romans 1:20, there is power in general revelation. God has revealed himself to people through what he's made. That's a starting point. They need to be able to break through the wall of atheism rationally. You can't just tell them, well, just trust Jesus and everything will be good. They go, huh? They won't go there, probably. But if you give them some good reasons to believe, then they will go there. God has allowed me to see a few examples like that, which keeps me going, frankly. There are a lot of people that just, they have this kind of response, but every now and then you see someone that the message gets through and it can change their life.
Is it Stephen Meyer? Is he the one out of Seattle?
Yeah, Stephen Meyer, yeah.
I heard an interview and he was talking about this, and I don't know if you have more on this, of computer programming and the analogy of genetics and the whole thing, and that these long sequences of computer program, and it just reinforces this whole idea that, a computer program won't work if there's just one small little error in that whole chain of things, and it's analogous to the genetic code, that you won't get viable life.
Yep.
And so you get that.
Absolutely right. Absolutely right.
And you're dealing with those statistical odds that are 1 times 10 to the huge numbers.
Yeah, you can take the mutation analogy and say, okay, take a functional computer program and just go ahead and make a random change in one line of code. See what happens.
That's why I didn't do computer programs. Because I
Yeah.
never get it right.
In fact, that was the gist of a lot of the early work that I said biologists poo-pooed. It were simulations like that, taking information structures that have the same level of complexity as a genome and saying, okay, just let's start making random changes throughout and let's see what happens to the information content, and then quantifying that. And the response from biologists was, well, you can have your stupid computers, but this is biology. It's different. Well, Doug Axe's paper pretty much blew that out of the water, because that's not different. That's a real protein. And it's the same principle.
At what point would someone say, there's these numbers that are so big, like with hitting the Scrabble board.
Yeah.
When does it represent impossible?
Yeah.
The reasonable scientist would say, wouldn't that be an impossible number? 10 to
Yeah.
the 40?
Yeah, it is. I don't have it in this PowerPoint, but I have a little back of the envelope calculation where I calculate the likelihood of just one cell coming about by random interaction, by random chemistry. And essentially, if I remember correctly, the numbers are 10 to the 340th something possible configurations of the proteins to make one simple cell that was really scaled down in complexity. And then if you take typical protein synthesis kinetic numbers to say, okay, how many of these configurations could you make over the course of the entire history of the universe? And it was something like 10 to the 15 or something like that. So 10 to the 340 compared to 10 to the 15. That's impossible. And that is zero probability.
Well, it isn't a cell an irreducible, isn't it like the mousetrap?
Yeah, it is in a lot of ways, because if you have a mutation, for instance, in a certain cell, then it becomes dysfunctional and maybe becomes cancerous. Yeah.
A cell is a little factory.
It is a little factory, right?
From just a bunch of swirling.
Yeah. Yeah. That's right. It is. Yeah.
You'd mentioned some challenges to the theory of
well, the irreducible complexity, what was the substance of the challenges?
Oh, for instance, a guy at UCSD named, what was his name? I can't remember now. Anyway, he took blood clotting, and he tried to show that if you take certain proteins away, the blood clotting mechanism still works. And for a while, that seemed to be having some traction, but then somebody did a really detailed investigation, and they found that it really is deleterious, and it will eventually cause the organism to die.
So the challenge was actually just to that particular example,
Yeah.
not to the whole concept.
No. And you have to do it. You have to take it one at a time, basically.
Yeah, there's so many examples.
Yeah.
What are they going to take sold them down?
Yeah, right.
It just struck me when you were talking about science having to be naturalistic explanations and such, that if you go back about 2 centuries and farther back, people really had a better grasp of what life was all about than we do today. I mean, what happened was when science came in and limited us to a certain way of looking at reality or existence, we threw out understanding by just common sense and observation, which we see in Romans 1 and 2, a whole lot. And we almost are dumber than we were back then.
Yeah, I mean, it's amazing to look at the list of people who developed modern science back in the 1600s and 1700s. I mean, you can look at them, and to a person, they were theists. In fact, the argument's been made that the reason modern science was born and thrived in medieval Europe was because of the theistic worldview that prevailed. And it didn't happen in other parts of the world like Asia because they thought that the universe was not worthy of study. It was ethereal and bizarre and not understandable, so why even try? But, you know, Newton, Kepler, Maxwell, Linnaeus, I've got a slide in another presentation. All the big people, all the big stars back in the 16, 1700s, they were all theists. Many of them were Christians, and it guided their science. Kepler had a great statement. He said, "We scientists are priests to the Most High God with regard to the book of nature." So we do our priestly work studying the book of nature and glorifying God through what we learn by that study. And that's how I view what I do. I'm a research scientist, and that's exactly how I view the career, the work that I have the privilege of doing. Is I've got the opportunity to study what God has made and see if I can learn something useful about it and make something useful out of it. And I count it a wonderful privilege. But yeah, and I think when you read Romans 1:20 and thereon, and how when you refuse to acknowledge the Creator for who He is, God does give people over to a depraved mind, and I think that's a real phenomena. And it's pretty scary when it happens, but I think it's quite true.
I read somewhere that, I don't know what type of Nobel Science Prize, it might have been physics, but 40 to 60% of the scientists in the 20th century who won the Nobel Prize were Christians. Wonder what exactly is there a debate going on in universities today about this issue? People of that stature who are winning prizes, are they allowing debates like that in our universities in America?
Yeah, I think they are in some places. I mean, take, for instance, James Tour. James Tour is a chemistry professor at Rice University, and he won the Nobel Prize in Chemistry a couple years ago. And he is very outspoken. In fact, if you want to see an interesting lecture, just Google James Tour and then look for his videos. He gave a lecture about a year ago that was really ruffled some feathers. It was in a church down in Texas, but he basically called people, origin of life people, on the carpet for their deceptive practices on what's been shown, what hasn't been shown on naturalistic origin of life. And he actually had to apologize to some people afterwards because he really got a little on his high horse. But what he was saying, I think, was basically true. He may have been a little edge to it, but he basically really, and people know where he stands. His personal website, It's just out there. He tells his students. So he's a little beacon in his microcosm there. And I think that's true for a lot of them. George Smoot at LBNL, who won the Nobel Prize in 2006 for cosmology, for the Big Bang cosmology, he has made some statements too that kind of indicate that he's on the theistic side. But people, yeah, if you win a Nobel Prize, you've earned the right to be heard, and you can say some things. And they Tour, yeah, James Tour.
Does that mean that doors are opening to increased debate and discussion of this issue, or are they closing? Sometimes we hear that people who hold creationist or beliefs are excluded from the university.
Yes, there are some really unfortunate situations where people have been believing scientists have been blackballed. For instance, Guillermo Gonzalez, who wrote the book The Privileged Planet. He was an astronomy professor at Iowa State, and he wrote the book, and then he went up for tenure, and he didn't get tenure. And it was claimed that it had nothing to do with, the decision had nothing to do with his beliefs on creation and such. But then the Discovery Institute, using the Freedom of Information Act, got a hold of the emails among the committee members, and they found all kinds of, I'd never give a creationist like that tenure, forget it, stuff like that. So that turned out to be a lie. But, so that has happened, it's very unfortunate. It's interesting though, when you talk to students in American universities, they, the more that they are censored from hearing opposite ideas to Darwinism, the more curious they get about them, and the more they want to know. And they don't like that. Most students, they want to know. They want to know both sides of the issue. And so if somebody tries to keep them from hearing the other side of the issue, that really ticks them off, and they make it happen one way or the other. So it's interesting. There are plenty of universities where it's open season on Christians, faculty and students, and you can really get badly persecuted for your belief in these things. But by and large, I think people are finding out about it, and it's spreading. Not only in America, but around the world. The intelligent design movement is now taking off on every continent, and there are clubs and conferences, and it's a really exciting time. And I would credit the good folks over in Seattle at the Discovery Institute. They've made it happen for the most part, and it's great. Yeah.
A little more on this. I think you'll get a lot more representation in the humanities of the universities that are opposed.
Yeah.
And with the new atheism, they've done different studies longitudinally over the last century where belief between sciences have remained fairly steady, even though the new atheism would have you think differently. But one area in particular that's shown a renaissance as far as Christian belief is in philosophy. And many of the top-rate philosophers throughout the country and the world are Christian. The Christian arguments for theism, design, they're holding water. And so that's one area where you're actually really seeing among philosophers that there's great respect for the theistic argument in philosophy.
That's good to hear. Yeah, Wayne.
There's a certain reputation that the young earth creationists, literal six-day type of thing, have gotten at this. Does the intelligent design movement have to put out some effort to overcome that negative reputation of anti-intellectual, anti-science?
Yep. Yeah, a lot of damage control having to be done. Anything else?
Oh, Ralph, could you clarify, do you get more flack from the humanities or less? More.
Yeah, I believe that. Yeah, in fact, it's funny because here's another, just a little factoid that's really interesting. Biologists, if you look at what they say to the public about Darwinism, it's just true beyond any reasonable doubt. Why would anybody doubt it? When you look at their private conversations, oh boy, many of them realize it's on thin ice, and in fact, the ice is cracking and breaking. And there was a conference a couple of years ago over in the UK at the Royal Society, sponsored, and a couple of the Discovery Institute guys got to go. And it was all about, we need to come up with an alternative mechanism beyond Darwinism because Darwinism isn't cutting it anymore. It's just failing miserably. And that was the whole conference was about. And this occupies many conversations. But oftentimes the people in the humanities, they will be the biggest champions for Darwinism. And I think it's because it's all worldview. They want to build this worldview, and Darwinism is, as somebody once said, allows you to be an intellectually satisfied atheist.
Well, and sin is in the humanities, it's not in the sciences.
What?
Sin is in the humanities.
No, there's plenty in the sciences too.
Well, I mean, it's in the field. It's
Yeah.
The whole idea of sin.
Oh, I see what you're saying. Yeah.
Holiness,
Right.
etc. That's
Right.
what the discussion of humanities.
Yeah.
That's why maybe.
Yep. In science departments, you see the word sin, and people think it's part of a trigonometry problem. Greg, you want to lead us in a song?
Okay.